Thanks very much for that kind introduction, and also thank you to Jason and the organizers for the invitation to speak today. I'm sorry that I can't be with you in person in Buffalo because of the upcoming government shutdown, but I hope that the conference has been a really great week. I'm excited to close out the meeting with our talk, sharing some of the research that we've been doing looking at sustainable aviation and how understanding aerosol emissions from aircraft engines can help us understand their effects on contrails and climate. So I live about 3 hours south of DC under one of the major skyways of our country. And as jets traverse up and down the East Coast, it's not uncommon for me to look out my window and see a sky full of these line-shaped linear condensation trails or contrails formed as the hot water vapor behind the jet exhaust cools and forms a cloud. And throughout the day, those line-shaped clouds transition into the thin, wispy cirrus cloud decks that we're often used to seeing. And so, an interesting question, perhaps best answered by models, is if the airplane hadn't flown through the sky, would that cloud have formed anyway? And if not, then there's a chance that it would have a pretty substantial impact on our world. And we know this is important because these clouds interact with Earth's radiation budget. And so they can reflect incoming solar radiation back into space. This has an effect of cooling the Earth, and it also dims the amount of light that comes down to the surface. And so that's important for things like solar voltaics and agriculture. But these are fairly thin, wispy clouds, and so not a lot of light is reflected back into space. And so the net shortwave effect is pretty small. However, these clouds are also very good at trapping outgoing thermal radiation and re-radiating it at the much colder brightness temperature of these high altitude cirrus. And so that's a net energy accumulation into the Earth system. And so that has a warming effect on the climate. And so in a recent assessment, David Lee and coworkers used sophisticated climate models to tally the climate effects associated with the aircraft fleet today versus the dawn of the jet age. And so what you see in these pie charts is the summation of the contributions for the greenhouse effect associated with aviation CO2 and actually a much larger effect for these non-CO2 effects. So the combination of those contrail cirrus clouds, NOx, and water vapor. And while it's worth pointing out that the non-CO2 effects are on par in the magnitude of a century's worth of aviation CO2 emissions, the uncertainty associated with these effects is much larger, very much in the same way that the uncertainty associated with aerosol cloud interactions overall is much larger than CO2 emissions. And so we need to understand what's happening here, but it also motivates the importance of these contrails and taking steps to potentially mitigate them. So if we want to look at individual flights or individual regions where we might potentially take action, that requires a different set of tools. And so this is a map from contrails.org, which is produced by Breakthrough Energy, showing the North Atlantic flight quarter. And so you're seeing the transition here from the beginning of the video at nighttime, the eastbound traffic, and now the reversal to the westbound traffic from Europe to the Northeast United States. And what they've done here is they've used the ECMWF weather forecast model in order to predict whether a contrail is going to form. And then they've also used a contrail prediction model to identify whether that contrail is likely to be warming or cooling. And so the warming contrails are given by the orange lines, and the cooling contrails are given by the bluish lines. And what we see is that the story is rather complicated. And so at night, there's no shortwave effect, and so all of the contrails are warming. And we see this cluster to the east of New England that's forming as the traffic leaves the country. And then as the sun rises, the animation lightens, we start to see the emergence of the shortwave effect dominating. And so we have some cooling contrails, actually where previously some of the contrails were warming. And so we need to understand what we can do to either avoid forming these warming contrails in the first place, or potentially take steps to make them less warming. Fortunately, there's a number of different pathways that we can explore in order to mitigate this so-called aviation-induced cloudiness. And so this chart shows some of the things that we could do potentially in the short term and the longer term, as identified by Bernd Kerker in a Nature Communications paper from a few years ago. And so while I'm going to focus this talk mostly on the short-term strategies, focused on advances in combustion technology and alternative fuels, there are other steps being taken. And so there's an active research program, and we've seen it in that map from the previous slide, to avoid forming contrails. If we can predict where they'll form, perhaps we can manage the air traffic in order to avoid them in the first place. And so while Kerker at 2018 identifies this as a long-term strategy, it's happening now. And so it may happen sooner than we expect. There's also things in here that are going to require quite a bit of technological development, things like liquid hydrogen and natural gas, electric propulsion, and flying in the stratosphere that are going to require decades to mature. It's also worth pointing out that this isn't just a climate story. Aviation emissions impact the air quality of communities around airports during that landing and takeoff cycle as jets are idling at the gates, taxiing to the runway, taking off, and then coming in on approach. And so this is a paper from Environmental Health Perspectives highlighting the effect of ultrafine particles east of Los Angeles International Airport. And what they did was that they measured the concentrations of these particles, and you can see the LAX plume as it moves eastward into the communities downwind of LAX. And so any efforts that we do in order to reduce the formation of contrails or the emission of particles is going to translate directly into improvements in air quality for these communities as well. So we and our partners have been looking at this for a number of decades, and while we're doing the same physics, the same experiments, the focus has shifted. And so in the 90s, the focus was on high sulfur fuels. So at the time, the concentrations in jet fuel of the fuel sulfur were approaching thousands of parts per million. And so these studies and flight tests tried to understand, given these high concentrations of sulfur, what would a modest reduction in sulfur translate to in terms of changing the contrail properties. In the early 2000s, we started to talk about alternative fuels, and these should be distinguished from the sustainable aviation fuels or SAFs that are commonly discussed today, in the sense that the alternative fuels can be produced from coal or natural gas via very much not sustainable Fischer-Tropsch processes, but their chemistry is very similar. And so during a series of ground tests using NASA aircraft that I'll talk about, we were able to refine the test methodologies that we use for understanding emissions and also get our first look at how these fuels perform. In the 2010s, we took to the air and actually studied the first 50% blends of sustainable aviation fuel to look at how emission reductions that we see on the ground translate to cruise altitudes. And now in the mid 2020s, we're looking beyond 50% blends to burning the 100% sustainable aviation fuel. And I'll talk about that research as well. But it's worth beginning where we started and some of the early tests in the 2000s with NASA's DC-8 aircraft, which was a workhorse aircraft for us for many years. You can see the aircraft here on the right. And what we would do is we'd chalk the airplane on the ramp out in Palmdale. We'd bolt probe stands to the tarmac between 1 and 30 meters behind the aircraft engine exhaust plane. We'd run a long sampling tube, usually around 40 meters off to the side, where we would safely position our instruments at the wingtip of the aircraft. And we'd run up the engines as the DC-8 burned different fuels. Jet A is the conventional petroleum-based fuel, and then we had a number of alternative fuels. And we'd measure the soot particles and total particle concentrations as well as other properties. And so I'm showing here the number of non-volatile particles emitted per kilogram of fuel burn. And so this is our soot particle emission index on a log scale on the y-axis, plotted versus engine fuel flow rate, which is our metric of thrust. And the points are colored by the type of fuel. And so the red points are our Jet A, petroleum-based fuel. The purple points are our alternative fuels. These are characterized by having near zero concentrations of of aromatics that are thought to be soot precursors, as well as near zero sulfur concentrations that are thought to be new particle forming precursors. And then the green and the yellow are the blends. And so what we see is that mostly we see a lot of spread here, but our highest concentrations are seen at idle. And then for this particular engine, as we increase the thrust to the intermediate powers, the concentrations decrease and then rise up as we approach the takeoff cruise. And we're able to see a factor of 2 reduction or so in terms of the soot particles emitted for the 50% blends, and a factor of 10 reduction in soot particle emissions for the pure alternative fuels. And the largest benefits are at those low power idle and taxi conditions where we're most concerned for air quality, but we're also seeing benefits at the high thrusts that are characteristic of cruise. We can also look at the size distribution, the microphysical information that measurements that were measured during this time. And what I'm showing here are the size distribution concentrations, dNd log dP, plotted versus the particle diameter. And the green and the blue curves were collected at 1 meter sampling probe distance. And so this is going to be too soon after the emission of the particles for us to form any sort of semi-volatile species. So these are our primary emissions of the non-volatile soot particles. And then the red and purple curves correspond to a probe position of 30 meters downwind. And so this gives time for the plume to cool and dilute and for semi-volatile species to condense to the aerosol phase. And so we see that same soot mode that we saw at the 1 meter probe position, but we also see this emergence of another mode, a nucleation mode, characterized by those volatile particles. And of course, if you're looking at this, you're probably noticing on a log scale that most of our particles are below about 30 nanometers in size. And so a key challenge here is how to measure the composition of these particles that are so small that they have almost no mass. And so trying to distinguish the fuel sulfur effects, the unburned hydrocarbons, and contributions from engine oil is a challenge that you'll see throughout the discussion in this talk. So given what we know about the emissions and the size distribution, what do we expect for contrail formation? And so it's worth reminding ourselves how contrails form. And so after the particles are emitted from the jet engine exhaust plane, the plume cools and water condenses onto the particles, liquid water. And so the process of contrail formation is not really one of ice crystal formation or ice nucleating particle activation so much as cloud condensation nuclei activation under very high water vapor supersaturations. And so particles activate into water droplets, which then freeze homogeneously and grow to form the large crystals that we're able to see in the visible contrail. And so since this is a CCN process, it's going to be governed by the Kelvin effect, the Raoult effect that we're familiar to seeing from aerosol cloud interactions talks. And so we would expect that the necessary relative humidity to activate a particle is going to decrease as that particle size increases. And so we're going to preferentially form our ice crystals or our water droplets on the largest particles first until we exhaust the supersaturation. And so the smallest particles are not going to participate. And so given this, and given the Kelvin effect, we expect that the contrail ice crystal should scale with the soot particle number, just from the ground test measurements. But of course, we need to get up into the air to understand what's actually happening at cruise conditions. And so I'll share some results for some recent flight tests that we've conducted over the past decade. The Access program, where we used the NASA DC-8 as the fuel burner and chased it with multiple aircraft from NASA, DLR, and NRC Canada. A follow-on test in 2018, where we used the DLR Atra as the fuel burner, and then some more recent work that I led where we used the DC-8 to chase a brand new pre-delivery 737 MAX. And I'll also note that I'm not going to discuss it for time, but there's been a lot of really excellent work conducted by DLR and Airbus over the last few years looking at very similar themes. And so for the access test, this is our fuel burner, the NASA DC-8 aircraft. It has 4 engines and 4 segregated fuel tanks, which is advantageous because we can have 2 different fuels in each wing and route them to all of the engines or separately as needed. We would chase it with NASA's HU-25 Falcon aircraft, and we'd fill the inside of the aircraft with aerosol and trace gas instruments. And the pilots would line up behind the DC-8 aircraft. They put the crown of the aircraft into the contrail plume and draw air in through an inlet that was able to sample the aerosol and trace gas measurements. And so as the plane rises up into the plume, the turbulence causes the airspeed to decrease. And so after about 20 seconds in the plume, the pilots safely lower the aircraft back down out of the plume, accelerate again, and then position it back up. So that's the view from the side. We can also see what the view from the front looks like. And so on the right panel, we're seeing the view out of the Falcon's front windshield. And on the left is some real-time data displays showing what the data looks like as it's coming in. And so you can see as the pilots put the crown of the aircraft up into the plume, we see enhancements in the particle absorption, the ultrafine particle number concentrations, nitrogen dioxide and carbon dioxide concentrations. And then they put the right wing in and we're able to measure the ice crystal size distributions with our cloud probes that are mounted on the right wing. And you can see that we're in a different regime that we're used to looking at with most cloud probes. We're actually getting ice crystal sizes at this distance that are submicron. And so we're challenging our instrumentation in our ability to accurately measure the size of these crystals because we're so close to the lead aircraft. And then they put the aircraft crown back up into the right inboard engine and we're able to sample the plume again. And so we can take the integrated plume area of our species of interest, our aerosol absorption as a metric for mass, our number concentration as a metric for the number of soot particles and total particles, ratio them to carbon dioxide to calculate those emission indices in terms of fuel burn. And what we find is that the strong emissions reductions that we see on the ground translate to cruise reductions. Burning the 50% sustainable aviation fuel blend has 50% of the aromatics, 50% of the sulfur, and that translates into a roughly 50% reduction in the soot particles being emitted per kilogram of fuel burn. And that translates into a proportional reduction in the ice particle number. And so this is good because as the number of ice crystals decreases in the cloud, we would expect the optical cross section to decrease and the climate impact should decrease as well. And we can compare this to models. And so this is some simulations conducted by Bernd Kerker, and similar work has been done by Fengshan Yu at SUNY Albany, using models to estimate what would we expect in terms of the number of nucleated ice crystals versus the soot particles. And for the recent test, the access test that I showed, as well as the more recent NDMAX test, where we're operating using older technology engines in what we call the soot-rich regime, where this relationship between ice crystal number and soot particle number is very linear. And so our results bear that out. But what Bernd's model shows is that as we get down into what he calls the soot poor regime, things start to look a little less, a little more complex. And so we're starting to see, instead of this single driving effect of the soot particles and driving ice crystal number, we're starting to see the impacts potentially of ambient particles serving as cloud condensation nuclei to form the contrail ice crystals, or co-emitted sulfuric acid and organic droplets, that nucleation mode that we saw from the ground test data that we could safely ignore because those particles were too small. Well, if we've removed the soot, maybe they become important as well. And so we really need data in this area of the graph to flesh out if where we fall, and also to inform the engine companies as they make design choices about where they're trying to achieve their emissions targets. And so we worked with Boeing, Steve Bauckham, a longtime AAAR participant, who handles their aviation emissions control work, connected us with their eco demonstrator program. And so he and I led a series of campaigns throughout 2021 and 2022 to sample the emissions, not from aircraft that we had easy access to, but were older technology like the DC-8, but now pre-delivery aircraft that were about to head out into the fleet. And in particular, we were interested in 737 MAX aircraft that have new lean burn combustor technology engines that are supposed to be some of the lowest sitting engines on the market. And so we drove our mobile laboratory, you can see down here in the bottom right corner, out to Seattle from Virginia. It was a long road trip. And we parked it right behind a blast fence. And so we're not having that long 40-meter tube that we needed for the DC-8 sampling. Now we have a short 4 or 5-meter tube coming through the blast fence. And we're able to sample the emissions coming from the engine. And so a typical test matrix looks like this. And so the y-axis, the red points are carbon dioxide mixing ratio on the left, the non-volatile particle number concentration given in blue on a log scale, and then the x-axis is time. And so as we step through increasing power conditions, we see a stepwise increase in the carbon dioxide mixing ratios that we measure through our probe. And initially, we see a similar stepwise increase in the amount of soot particles being emitted until the engine transitions into the high power staged combustion mode, which is where it operates fuel lean, and we're expecting the soot particle emission should be the lowest on market. And we see this precipitous drop, and remember, this is on a log scale. So this precipitous drop in soot particle number that stays low even as the CO2 continues to march up. And so again, we can take the ratio of the species of interest to our CO2 in order to compute an emission index. And that's what's shown here. So on the left axis, we have our non-volatile soot particle number emission index, number of particles emitted per kilogram of fuel, plotted versus our engine thrust metric. This is the engine fan speed. And so idle conditions will be down here on the left, and climb and takeoff conditions will be up here on the right. And each of the colored points represents a different fuel that we investigated. So the white points are the 100% petroleum-based Jet A. The green points are the 100% sustainable aviation fuel that has near zero aromatics and zero sulfur. And then the red and the blue points are the 30% and 50% blends. And I'll note that even though these blend ratios are intermediates, we use different Jet A's to blend them. And so the aromatic and sulfur concentrations don't scale linearly with the blend ratio. So what do we see? Well, we see a huge effect on soot associated with that engine staging. And so initially our soot particle emissions are up in 10 to the 14, 10 to the 15. And when the engine stages, it reduces the number of soot particles coming out of the engine by a factor of about 1,000. And then within the different engine operation regimes, we're seeing benefits transitioning from the white points, the Jet A points, to the green points, the 100% sustainable aviation fuel. And so we're seeing the best of both worlds here for soot, the cleanest burning fuel in the cleanest burning engines at these high thrust conditions. When we look at the total particle number concentration, we see a slightly different story. And so here we see the similar behavior for the 100% SAF. Again, we're seeing this effect of the engine actually reducing the number of total particles. So this is the combination of soot particles and volatile particles like sulfuric acid and organics at the high thrust conditions. But for the Jet A, which has that high fuel sulfur content, we're seeing high particle emissions across the board. There doesn't seem to be an effect. And I'll also highlight that the scale on the right axis are an order of magnitude higher than on the left. And so we're producing a lot more volatile aerosols than we are soot particles. But of course, we know that the size distribution is going to be controlling here on whether these matter for ice crystals. So let's take a look at that. And so this is an example from the 23 ground test at 75% N1 thrust conditions. So this is the high thrust staged conditions. And what I'm showing are background subtracted DND log dp aerosol concentrations plotted versus particle diameter. And so these are the total particle number concentrations for two different fuels, our Jet A fuel given by black and our 100% sustainable aviation fuel given by the green. And so we see a similar size distribution structure for the Jet A that we saw perhaps for the DC-8, this large nucleation mode, and then another smaller, more modest soot mode that tails off towards larger sizes. And when we burn the 100% sustainable aviation fuel with the 0% aromatics and 0% sulfur, we're able to effectively eliminate this nucleation mode. But we see that the larger particles persist. There's a lot of similarity here in the 20 to 40 nanometer size range in terms of concentrations. And so we'll see when we get up to cruise whether this translates into a difference in the contrail formation potential. So we took to the skies of Seattle in a flight test conducted in 2023. Here we're using the DC-8 as the chase aircraft rather than the fuel burner. And so you can see some of the inlets that we've mounted on top of the aircraft and on the windows. Our lead aircraft is a pre-delivery United 737-10 aircraft that Boeing provided. So this is a two-engine aircraft. It's got segregated fuel tanks, and so we were able to have the 100% sustainable aviation fuel in the wing tanks and the 100% Jet A fuel in the center tank. And so we were able to burn both fuels during a single flight. And so that's really important because it allows us to take into account differences in meteorology from day to day. And so our forecast team would look at the weather forecast to identify the areas of the Pacific Northwest that we thought would be most favorable to contrail formation. And then we join up the aircraft in the skies over Montana or Washington State or Oregon in order to sample the contrail and the jet exhaust behind the 737 MAX. And so because of as I showed before, the ice crystal sizes when we're very close to the lead aircraft are submicron, very small, which really challenges our cloud probes. And so in order to give the ice crystals in the contrail time to grow big enough that they fit within our cloud probe sampling regime, we actually sampled 4 to 5 miles in trail of the lead aircraft in order to have those measurements be within the sweet spot of our existing technology. And so that's a gap. We'd like to be able to have technology where we're able to measure submicron ice crystals. You see the team inside the NASA DC-8 walking around, comparing instruments. Here's the collaborators from DLR who were working on the cloud probes and the trace gas measurements. And so the pilots would position the aircraft above the contrail. They'd maneuver the airplane just above the turbulent wake vortices that were a hazard for us. And they descend just skimming the tops of those wake vortices. You can see us coming down through the 45-degree camera that was mounted on the belly of the DC-8 aircraft. And so then we would draw in the trace gases and the particles through the probes that were mounted on the side of the aircraft through window blanks, as well as the crown of the aircraft. And then we had a variety of cloud probes mounted on the top and bottom of the aircraft as well to measure the contrail microphysical properties. So a similar video to before showing the view from the front of the airplane through the cockpit. And on the left now, we're looking at the relative humidity with respect to ice and water, and the number concentration of particles, as well as the trace gas species on the bottom. And you're seeing that we have this really nice persistent contrail. We're existing in a supersaturated environment with respect to ice. And so the contrail extends all the way back to where the DC-8 is sampling it until we cross an air mass boundary. And now the lead aircraft is still forming a contrail, but the relative humidity with respect to ice in the ambient environment is below 100%. And so it actually sublimates before it gets back to us. And so both of these conditions are really interesting to us for understanding the contrail dynamics and how we model that. Although, of course, the persistent contrail is the one that is most climatically relevant. In addition, we're interested in understanding the particle emission indices and trace gas emission indices. And you can see that even though the pilots don't have that visual cue of the contrail extending all the way back to where the aircraft is, they're still doing a really good job of putting the aircraft into the plume in order to get these enhancements. Okay, so what does the data look like? So I thought I'd show a short time series here of what the data looks like to us as it's coming in real time. And so the top trace here in yellow is our carbon dioxide mixing ratio. The purple trace is our contrail ice crystal number concentration. The blue trace is our total particle number. And so this is both the soot particles and the volatile particles. And then the red trace is our non-volatile soot particle number concentration. And it's very clear as the pilots position the aircraft into the plume, we see enhancements in our CO2, in our total particles. Depending on where we are meteorologically, we also see a corresponding enhancement in ice crystal number. But the soot particles are noisy, but there's not that same relationship where we see enhanced soot particles above the background. And so this is a good problem to have. We're actually struggling to see and to measure at these distances the number of soot coming out of the engine. But we're also highlighting that there must be other particles that are stepping in to play a role in forming these ice crystals. And so we can use the soot particle emission indices we got on the ground, since we weren't able to get the above signal to noise measurements at cruise for our x-axis. And we had good ice crystal numbers measured at cruise. And so we're able to now add a circle for the eco demonstrator results to our character plot, showing that we're falling roughly within this regime. So we're above what we would expect for an ambient background, but we're below what we might expect if all of those nucleation mode particles were contributing ice crystals. And so what this points out is that we may need to consider going forward, not just efforts to reduce soot particle emissions, but also efforts to reduce the formation of these volatile aerosols. And so if we could take steps either via engine technology changes or fuel composition changes to drive those volatiles down, we should be able to decrease this yellow circle even further. And so towards that end, and one of the areas that is ripe for intervention is looking at the way aircraft engines handle their oil. And so these are complicated, high rotational speed, hot turbo machines that need to be lubricated. And as they're flying along, the gearbox and other lubricated parts are vented to the atmosphere in order to equalize the pressure. And so while the engine companies design oil recovery and oil separation technologies, including cyclones and centrifugal separators in order to recover most of the oil, some of it still is vented out in those breather vents. And so you can see an example here for an engine that we tested in 2022, where the oil breather vent on the bottom of the engine nacelle, we've attached a hose in order to duct the hot breather vent oil out to the side. And you can see this wisp of white smoke off to the left here, which is that mist of oil droplets. So this is one design. The design associated with the LEAP engines that I showed you in the previous slides doesn't vent the oil on the bottom of the nacelle. It actually vents it at the tail cone. And so you can imagine this oil vapor getting mixed with hot combustion gases at the center line of the aircraft engine, vaporizing and then recondensing onto particles, or in the absence of an appreciable condensational sink for condensation, nucleating new particles. And so we took steps during this ground test in order to divert the oil away in order to study what the emissions look like when it's diverted and when it's not diverted. And Ben Nault, who's at the meeting from Aerodyne Research, gave a really nice presentation, I'm sure, yesterday, Thursday, talking about some of these results and the measurements that they made with their aerosol mass spectrometer. In another similar test, we partnered with Gulfstream and the FAA to measure the engine exhaust behind a Gulfstream G700 aircraft that was burning 100% Jet A fuel as well as 100% sustainable aviation fuel. And again, applying a very similar methodology, attaching a tube to the oil breather in order to divert that organic vapor off to the side of the test. And so we're able to measure the contribution of the oil relative to the fuel components. And you see an example size distribution up here showing very similar results to what we saw for the Eco Demonstrator campaign. For the 100% Jet A fuel, we see this bimodal size distribution. In this case, we have a lot more soot. And so the soot concentrations are on par with the nucleation mode particles. And when we transition to the zero aromatic, zero sulfur sustainable aviation fuel, we eliminate that nucleation mode entirely and reduce the soot mode considerably. And so Sergio Dominguez Medina from NASA Glenn had a nice poster about this, I'm sure, earlier this week, talking about the results from the Gulfstream test. So everything I've shown you so far has been in situ measurements, where we take a chase aircraft up or we position a mobile laboratory with a probe behind the aircraft and run up the engines to measure the emissions of particles and contrails. We're also exploring how we can use remote sensing technologies in order to uh, interrogate the structure of the contrails without having to put a chase aircraft into the plume. And this has a number of advantages for us from a safety of flight perspective. As you can imagine, the coherent rotating vortices of the engine exhaust present upset hazards. If the aircraft were to position itself into one of these rotating vortices, we could easily find ourselves getting spit out and upside down. And so being able to sample this above the plume where we don't enter into that wake vortex environment has some advantages there. And so we're using, in this case, a high spectral resolution LiDAR. And so LiDAR operating very similar to the commonly understood radars. Instead of sending out sound waves and measuring what is reflected back, the LiDAR is sending out a laser beam and measuring the light that is backscattered back. And so you can see the image here on the right. The bottom of the DC-8 here are in situ cloud probes mounted on the belly of the aircraft. And we're viewing the contrail through the 45-degree camera. And so the 737 is off in the distance and the contrail is extending back to our position. And so the left figure shows the cross-sectional image of this contrail. And so the y-axis is the vertical cross-section in feet. And the x-axis is the horizontal cross-section, actually in time. And so you can imagine the pilots starting on the left side of this plume and then dragging the laser slowly across the plume in order to get a horizontal cross-section, and then grabbing the aircraft back. And so we see the structure of the contrail that we're able to see from our pictures, this very coherent rotating vortices, and then the formation of this secondary wake that detrains from the top of those vortices. And so you can imagine if you're one of the DC-8 pilots, you're viewing this in the distance, you're trying to position the aircraft right about here, trying to keep the DC-8 wings out of these vortices, but also get our sampling probes and inlets into the topmost part of the plume. And so this is a typical time series showing the aerosol light extinction measured by the LiDAR. So the y-axis is altitude. You can see the DC-8 flight altitude given by this purple line. And the x-axis is time. And so as we're flying along, the aircraft crabs across the contrail and we get a cross section, and then we get another cross section. And so each one of these encounters corresponds to a cross-sectional image like I showed you before. You can also see natural cirrus just below us. And so one of the challenges of conducting these experiments is that oftentimes the conditions that are ideal for forming contrails are also ideal for forming natural cirrus clouds. And so this uh, is a challenging environment for the both aircraft to be flying in, where the separation between the naturally occurring cirrus and the contrails is actually very, very close. But the LiDAR is able to very precisely differentiate these very intense cloud plumes from the more wispy cirrus. And so proving this concept during the 2023 Eco Demonstrator campaign, we had a follow-on campaign in collaboration with GE Aerospace, where they brought their large 747 flying testbed out to Langley, and we chased the aircraft with our Gulfstream 3. And so this aircraft combination would not be good for doing in situ sampling. The Gulfstream aircraft with its T-tail is thought to not be structurally strong enough in order to enter the wake vortices, especially behind a large aircraft like a 747. And so using now this remote sensing technology, as shown in this stylized image from NASA Langley, really allows us to remotely probe the structure of the contrail and potentially relate changes in the contrail structure back to changes in the engine operation or fuels. And so you can see, again, a very similar structure, these coherent vortices that roll up the ice crystals on the bottom left, and then the detrainment of the secondary wake. Okay, so to sum up, um, I hope I've convinced you that we as aerosol scientists are a pretty critical link for connecting the aerospace engineering design choices being made by airframers and engine companies to the emissions of particles and trace gases that ultimately have atmospheric impact, both for air quality and for climate altering contrails. I've shown with our recent work that advancements in engine technology, particularly these lean burn uh, combustor technologies that we've sampled so far, and also some new engine technologies that are currently being brought to market by other engine companies, are game changers in terms of the number of soot particles being emitted. And we see even additional benefits from burning these zero aromatic, zero sulfur sustainable aviation fuels. And so this is an ideal best case scenario, very much in line with where we expect to be sometime in the next 20 to 30 years. But it's also worth pointing out that we're nowhere near burning 100% SAF in the commercial fleet at this time. In fact, the production targets are just a minuscule amount of what we need for the global jet fuel supply. And so we're really in testing these 100% pure sustainable aviation fuels, looking forward a few decades in advance. We're also looking at the quantitative reductions in the ice crystal numbers, and we see that the particle numbers are reduced. And so we should take credit for that. The engine companies should take credit for producing a low soot engine that has contrail benefits. But it isn't a proportional reduction. And so those sources of volatile particle emissions, whether it's from the fuel or whether it's from the oil system, need to be looked at, and there's still potential gains to be had there. And this is something where we as the aerosol science community can come in, is that we need to better understand the composition of these nucleation mode particles and differentiate where are these particles coming from. Do you need a certain amount of fuel sulfur to nucleate that small aerosol mode? Or is that going to be replaced by the presence of that condensable oil vapor anyway? And so understanding where we can get the biggest bang for the buck in terms of reducing the volatile aerosol production is an important research question. We're also exploring new research methods for remote sensing, and so that we don't have to have a chase aircraft in the plume. That really limits the number of aircraft that we're able to use for these research purposes. And particularly as newer aircraft come online that replace the old aircraft, like the DC-8 that were built using basically with large safety factors, we're starting to see that the newer aircraft that we may have access to are closer to our structural tolerances than they have been in the past, and may be unsuitable for the sort of in situ chase plane experiments that we've been traditionally doing. And so these remote sensing techniques are likely to be a stronger influence in our data gathering going forward. It's also important to recognize that even though we're looking at burning sustainable aviation fuel, it's still a carbon-based fuel. We're looking beyond that to non-carbon-based fuels and things like liquid hydrogen gas turbines that would be zero, potentially zero soot emitting. But also we've shown, based on the oil emissions, that these are still gas turbines. They still have lubricating oil and they're still going to emit particles. And so studying how these low soot engines perform informs our expectations for those low or no soot engines that may come on the market in the future. And I didn't talk about it much during this talk, which was very aerosol focused, but I highlighted at the beginning the work of Breakthrough Energy and some of the other folks who are trying to simulate and forecast where contrails will form. And so there's also an effort to potentially forecast and identify where contrails will form and reroute aircraft to avoid forming them in the first place. And this is seen as potentially low-hanging fruit for eliminating a pretty potent near-term climate forcer. So much so that earlier this year, the European Union mandated that all aircraft operating within the EU from EU airlines have to monitor, report, and verify whether or not they're forming a contrail. And so this is seen as laying the groundwork for potential future regulation of contrails. And there's a lot of efforts to conduct trials and see how easily this can be accomplished in what are often very congested airspaces. So I thank you for your attention. Again, I'm sorry that I couldn't be with you for what I'm sure was an outstanding AAAR conference this year. If you have any questions or comments, I would welcome you to email me at my NASA email address, richard.h.moore@nasa.gov, and I hope to be able to respond after the government reopens. And then finally, I'll just leave with a plug. If you're interested in this topic and would like to know more, the National Academies conducted a consensus panel and report writing exercise earlier this year. This was chaired by Tim Llewellyn at Georgia Institute of Technology, and included a number of people on the committee, myself included, looking at what research is needed related to contrails and climate impacts. And you can scan the QR code on the bottom right to download a copy of the report. Thank you.